So there are two classifications of atomic weapons. There would be your atomic bomb and your thermonuclear device. The A bomb or atom bomb was used on Hiroshima and Nagasaki. Fortunately, a thermonuclear device has not been used in war. In order to understand how the thermonuclear device works, we first need to understand how the A bomb or atomic bomb works. And this comes to the idea of uranium enrichment, which I discuss in the nuclear fission video. The idea that we shoot a neutron into uranium-235 and it splits into a nuclear reaction. As we discover uranium naturally in the Earth, it is primarily uranium-238 with a little bit of 235 in there, and therefore this is ineffective in terms of making a reaction. So we use a complex processes that involve some centrifuges, and what we end up doing is we are able to get a substantial amount of uranium-235 with a little bit of 238 lingering around. We fire that neutron, we hit 1, and that begins a chain reaction that causes all the others to go, or almost all of them. Now, in a nuclear power plant, we would not want to be enriched to this level that I have here. If I did this, that nuclear power plant would blow itself to pieces, as well as the city that it is in. So enrichment levels for, say, a nuclear power plant versus a nuclear bomb, nuclear power plant is anywhere between 1 to 10% enrichment, and then nuclear bombs are around 90% enrichment, and we call that weapons grade uranium. Just a terminology that you've probably heard before. So what is the whole idea about how to make this bomb work? Here is a diagram of Fat Man. Fat Man was the bomb that was dropped on Nagasaki. It was the second one. The first one was Little Boy, and Little Boy was on Hiroshima, and that was a uranium bomb. The plutonium bomb on Nagasaki was Fat Man. The idea is, inside of the bomb, we have something that will emit neutrons, and we surround it by plutonium. Now, if we come back to here, it's very similar, where instead of plutonium we have uranium, but one of those neutrons goes off and hits the plutonium, it begins the reaction. Now, why isn't this bomb just going to go ahead and detonate itself on its own? Well, because this plutonium is actually hollowed out. So it's spaced out enough. We're distributing the volume over a much bigger area in a fashion that will prevent the chain reaction from occurring. So when we want to detonate it, what we have is we have a conventional style of explosive devices that are surrounding this whole thing. And when we trigger those conventional explosives to detonate, it causes the hollowed out plutonium or uranium core to collapse in on itself and on top of that neutron emitter. That causes the chain reactions to begin, and when the chain reactions begin, they can't be stopped, and it goes boom. So that's how the atomic bomb or A bomb works. How does a thermonuclear device work? Well, the thermonuclear device involves taking hydrogen and hydrogen and smashing them together, and the result is you get helium. Well, this is very difficult to do because hydrogen has a natural positive charge in the nucleus, and therefore you have, although a velocity trying to get these two things collide, you have a very strong electric force repelling. So the hydrogen and hydrogen atoms naturally don't want to be close to each other. So we need to get those hydrogen atoms to move at incredibly fast speeds to overpower the electrostatic repulsive force. How do we get them to gain that high velocity? Well, thermodynamics tells us that temperature is really nothing more than a measure of the kinetic energy of the atoms and molecules. And to remind you, kinetic energy is 1/2 mv squared. So if we get the hydrogen to be extremely hot, we've increased the kinetic energy of the hydrogen, which means the hydrogen atoms are moving at very fast speeds. Well, how do we get them to move at very fast speeds? How do we get them to heat up? Basically, the thermonuclear device is a small atomic bomb that's sitting next to a bunch of hydrogen that's ready for nuclear fusion. We detonate the uranium and plutonium, and then that generates the heat required to begin the hydrogen fusion process. When the hydrogen fusion process begins, we have essentially created a mini sun on the Earth. This is what the sun and all the stars do, is they take hydrogen and they fuse it with more hydrogen. They don't do so by detonating uranium or plutonium nuclear devices. It's actually done by the immense gravity. The incredible amount of gravity in a star is enough to give the hydrogen atoms enough kinetic energy and therefore enough velocity to collide naturally on their own. And when they do, they fuse together and form helium, as well as give off a tremendous amount of energy. The biggest benefit that we could have in society is if we were able to create nuclear fusion instead of in a bomb, but we wouldn't need the uranium or plutonium, and we could create it stably in a lab, is the amount of power we would get. It would be an incredible amount of energy, enough to power the entire planet for the remaining duration of human civilization. The downside is we don't know how to get, at least not at the moment, how to get the hydrogen to be hot enough to naturally fuse itself without using something like a uranium or plutonium bomb. That's not going to be effective, though, because you don't want your power plant to turn into a thermonuclear device. There's been many attempts, primarily with the use of magnetic and electric fields, but again, in order to get hydrogen to fuse with other hydrogen, you need temperatures in the millions upon millions of degrees. And the reason why those nuclear reactors are therefore naturally unstable is most things are not going to remain in their current state of matter when they're heated up to several million degrees.